Okay, so now we're going to do the particle in a box. And here I have my diagram. What this means is that I've got the particle existing here with a mass m from dimensions, and this is the x dimension. So from 0 to a box length a. I think Atkins uses L. I will use A. Deal with it. So E sub P, this is the potential energy, is equal to 0 inside the box. And this is kind of a weird box. Use your brain for a second and think about how what we're building towards is we've got this proton and this electron, and it's bound by some Coulombic potential, positive and negative. Okay, and they're going to attract each other, but they're going to attract each other to an extent, but they're not going to attract each other too much because then they annihilate each other. And so there's a potential energy, i.e. Coulombic, that's keeping this electron bound. Okay, so what we're going to do is we're going to build up our model the simplest possible system, no potential whatsoever, and instead of it being bound to this proton by this potential, we're just going to bind it to a box. Go team. And so we're going to see what happens with applying the Schrodinger equation and playing with the wave function for this particular case, such that we can gain the skills to when we actually look at the electron bound to a proton, which is the hydrogen atom, which gets us to the atomic orbitals. Okay, so we've got our proton or electron. It's bound inside a box. On each side of this box, the walls are an infinite potential, which is like you are in an infinite well. And you're looking up and you're the electron and you're like, I can't get out because it's infinitely high. There's no way you can get out. If it were like this and it was a semi-infinite well, like not quite, and you're like this and you're like, if I can jump high enough, I could get out. It's not the case. There's no possible way that this electron can get out, which means that it has 100% probability of being found inside this box. Okay, so we're going to use the Schrodinger equation. H psi of x is equal to E psi of x from the interval 0 to, x to a, which means x can be anywhere from 0 to a or anything in between. All right, so my Hamiltonian is equal to minus h bar squared over 2m d squared dx squared plus 0, because my potential energy inside the box is 0, psi of x equal to E psi of x. Okay, just like before, well, so what we're going to do here is we're going to just kind of rearrange this a little bit to where I've got d squared dx squared psi of x is equal to, I'm going to move this over here, minus 2me over h bar squared psi of x. Okay, and for convenience, and you'll see why in a little bit, I'm going to rename this 2m e over h bar squared. I'm going to call this k squared. So we're k squared equals 2me over h bar. I'm not sure why I have, h bar squared. There we go. Okay, and that's just for convenience. So just like we did with the free particle, now I'm going to guess a wave function, smartly though, and I'm going to say that my wave function is equal to a cosine x plus b, erase that, a sine kx plus b cosine kx. Now you might be asking yourself, how would you know that? And the answer is only through experience. I know that my particle is going to have wave-like behavior. And so if you add, so a sine function is a wave, a cosine function is a wave. I've got a superposition of two waves here. And so we're going to apply what are called boundary conditions to investigate what these two coefficients a and b might be, and you're going to see the importance of boundary conditions. The whole purpose of this system is to show you boundary conditions matter. Okay, so since the probability of, so what is a boundary condition? Well, at the boundary, which is right here, so here's a boundary, this bit, and this bit. So at the boundary, the probability of finding the particle is 0 outside the walls. So over here and over here, the probability of finding the particle is 0. And so for psi of 0, that gives me a sine k times 0 plus b cosine k times 0. And so this equals 0 because at the boundary, we have to, so right here, at psi is equal to 0, the particle cannot exist. It's an infinite potential. It'd be like you existing in the wall. Not happening. So sine of 0 is 0, but cosine of 0 is 1. Ah, go team. So B equals, well, this is just equals B because this equals 1. And so that means psi of 0 has to be 0, which means B is 0. Yay! That's awesome. B is 0. Well, this just got simpler. So that means that my wave function, psi of x, for a particle in a box based on boundary conditions is equal to a sine kx. Cool. Let's consider the other boundary condition. At x equals a, so this is at x equals 0, boundary condition 1, boundary condition 1. It's boxed because it's important. Boundary condition 2, boundary condition 2, x equals a. So psi of a is equal to a sine k times a. But we know, just like with this condition, psi has to be 0 at this condition as well. So that means this equals 0. Ooh, what does this mean? Well, sine k times a equals 0 if and only if k times a is equal to some n pi. Okay? It really helps to think about your unit circle. Okay, so here's sine of x. Here's so we've got pi over 2. Whoops. That's a lie. We've got pi, 2 pi, 3 pi, 4 pi, and here's pi over 2. Okay, so every time it crosses the 0, this really isn't the unit circle. Whoop, here we go. So here, so the sign is going to be the y component. So anytime we're here or here, so there's pi, here's 2 pi, pi, 2 pi, we're going to have 0. So that means that n can be, oops, so n equals 1, 2, 3, and so on. So anytime you have n equals 1, n equals 2, n equals 3, you have that moment where all of a sudden the boundary condition is satisfied that psi of a is equal to 0. So now we've learned more about our wave function with what our boundary conditions require. Does that make sense? So now, this means that psi of a is equal to a sine n pi. Oops. So solve for a then. So a is equal to n pi over k. Actually, let me make sure I want to do this right. Actually, pause for a second. Okay, sorry, I lost my train of thought. Okay, so we know that our condition is satisfied then when Ka equals n pi, okay? But recall earlier that I said that K squared was going to be equal to 2me over h bar squared. Well, I'm just going to take this condition based on my boundary condition, and I'm going to say K squared A squared is equal to n squared pi squared. Go team? What this means is now I can impose, so I can solve for K squared, and it's n squared pi squared over A squared. And if I now put this into here, I'm left with E, and solve for E, you have to do some of this on your own, is equal to h bar squared n squared pi squared over 2ma squared. Go team! What does this mean? And I'm going to simplify this a little bit. So keeping in mind that h bar is equal to h over 2 pi. So I can simplify this a little bit more and say E is equal to h squared n squared over 8ma squared. Okay, what does this mean? It means that under the conditions of the particle being bound by an infinite potential from 0 to A, the energy levels here, the available energy levels are now h bar squared dependent on the size of the box. That's kind of cool. But also, they have a condition now that they are restricted to integer values of n. So n equals 1, 2, 3, and so on, any integer, E will then equal h squared n squared over 8ma squared. So the energy for n equals 1 will be h squared over 8ma squared. For n equals 2, h squared 4 over 8ma squared. If this is 3, this value would be 9. So you've got these values, discrete quantized energy levels based on the boundary conditions. Think back to the free particle. We didn't have quantized energy states because there were no restrictions based on the boundary. Phenomenal. Go team. These are quantized energy states. Woo! Go team. Quantized energy states. Okay. Cool. All right. The next part, we're going to figure out what this A is, because I'm assuming I've talked for way too long. We're going to figure out what this A is, and then we're going to plot this in terms of psi squared to look at what the wave function itself looks like in terms of the probability density. Yay! All right. Stick around for Particle in a Box Part 2.